Hello and welcome to Precalculus lesson number 29. In this video, we're going to learn about the applications and models of exponential growth and decay. Some of the topics you will see will be reviewed, but it's always a good idea to visit mathematical topics more than once for optimal absorption. Exponential and growth decay functions are necessary because certain quantities observed in various sciences, ecology, biology, or even economics and social sciences, they change that means either grow or decay at rates that cannot be adequately captured using linear or polynomial functions. This type of growth or decay is referred to as exponential growth and exponential decay. So when you hear that word in your mind, you're probably associating it with very fast, right? And you wouldn't be wrong, right? It would be very fast growth or decay. Exponential growth and exponential decay commonly occur according to the following formula involving the number we've already learned about, the Euler number, which is approximately 2.7 in value. So the formula is very simple. A of t equals a0 e to the kt, where t is the time period of growth or decay, and k is the exponential growth rate if it's positive, or decay rate, exponential decay rate if it's negative. Now, again, when k is greater than 0, the function a of t describes exponential growth. An example of that, which we've already seen, is compound interest. And when k is negative or less than 0, then the function a of t given here will describe exponential decay. An example of that is radioactivity, which we'll look at next. All right, suppose a sample of 400 grams of radioactive lead-210 decays to polonium-210 according to the function a of t equals 400 e to the negative 0.032 t, where t is time in years. We want to find the amount of radioactive lead remaining after the following periods of time. Now, we know that basically we're going to be applying the same function, right? We're just going to be replacing the t with 3, 6, and 10 in the first three parts of this problem, right? So we want a of 3, which is simply going to be 400 e to the negative 0.032 times 3. We want a of 6, which is 400 e to the negative 0.032 times 6. And a of 10, the amount after 10 years, which is going to be 400 e to the negative 0.032 times 10. Now, the nice thing about our calculator is we won't have to really enter all that 3 times, as you'll see. Okay, so for part 1, we're just going to enter 400. And remember, a quirk of this calculator when you multiply by powers of e is that you have to put multiplication sign, otherwise it doesn't work properly, it gives you an error. So we're going to go Shift ln, that gives us e to the power of, it's ready for the exponent, so we just put negative 0.032, and we're going to multiply by 3. We can just use the parentheses feature here and then just put 3. All right, so we can see that the amount left after 3 years is approximately 363.4 grams if we just round to the nearest tenth. Now for the next part, the nice thing is you can just double click that, it copies it, just place the cursor right after the 3 and delete the 3 and replace it with 6. So we get, for after 6 years, the amount left will be approximately 330.1 grams, rounded to the same nearest tenth. And then for the next part, of course, we're just going to do the same thing, except we're going to replace the 6 with 10. Always take a few seconds to make sure you've typed in everything correctly. I say it and don't always do it, but I try to remember to always do it. Okay, so There we go, and it's correct. So you can see that about 290.5 grams will be left for after 10 years. Okay, so the next thing that we're going to look at is going to be a little bit different. Here we're finding the half-life. Remember, the half-life of a substance is the amount of time that it takes for a given amount of the substance to become half that given amount. So here, when we start with our general formula, A of t equals 400 e to the negative 0.032 t, we're going to be interested in the time that it takes for this 400 to become 200. So we want the future amount to be half of that, which is 200. So we get 200 equals 400 e to the negative 0.032 t. And the trick here is to solve for t. Since we want to isolate this factor right here, this exponential factor, we're going to go ahead and divide both sides by 400. So we get 200 over 400 equals, on this side, of course, 400 divided by 400 is 1. So we just get e to the negative 0.032 t. And 200 over 400, of course, is 0.5, right? Or 1/2, whichever you like. All right, in order to solve this, you need to remember that the exponential function and logarithmic function are inverse functions. So basically, if we have e to the negative 0.032 t, and we want to bring that negative 0.032 t out of the exponent position, we're going to have to apply the inverse function, which is log base e of that to both sides. Now remember, that's just ln of e to the negative 0.032 t, and of course ln of e to the negative 0.032 t, because of their inverse relationship, is just going to be negative 0.032 t. So that's what we're going to do to both sides. We're going to apply ln to both sides. So we get ln of 0.5 equals ln of e to the negative 0.032 t. Remember, ln stands for natural logarithm. All right, and here we get ln of 0.5. We don't really have to have the parentheses there. And we get equals, as we just discussed here, is just going to become negative 0.032 t. So now we just divide both sides by negative 0.032 and we solve for t. So we get t equals ln of 0.5 over negative 0.032. So now we go back to our trusted friend here and we just type it in. So I'm going to put the entire numerator in parentheses. So I start with parentheses, then I put ln of 5. Now we're going to have to exit both of those parentheses and then hit the division sign. And then we'll put negative. And remember, you have to use this button if you want to use the negative sign as a sign of a number, right? Only use this if it's a subtraction you're handling. So this means minus, this is negative, right? So we get negative 0.032. Okay, we hit enter. I can see, hold on. If I take my second to double check, I just realized, because I always do that even visually, if not necessarily verbally talk about it, to double check, and I see I put in 5 when we should have put what? 0.5. So always check. All right. So ln of 0.5 over negative 0.032. So there's the correct answer. So t is approximately 21. Now, of course, we realized here something is wrong. You should have realized it anyway, because time can't be what? Negative. So I realized immediately, oh, I must have typed something in incorrectly, and indeed that was the one. So rather than redoing the video, I decided to let you see that we're all human. Okay, so but if, as long as you're careful and you double check, you'll catch those human errors. So here we'll just go to 0.7. All right, so it'll take approximately the half-life of this radioactive lead-210 is approximately 21.7 years. Okay, and again, remember what that is. That's the amount of time that it takes for that substance to go from a given amount to half that given amount, right? So there you have it. All right, so it's very simple but important problem. Make sure you understand it and we'll proceed. All right, so here we're given that if 14 grams of a radioactive substance are present initially and 9 years later, only 7 grams remain, how much of the substance to the nearest tenth of a gram will be present after 14 years? So as you can see, we are not given the growth rate or the in this case the decay rate, right? So we need to find that first, the K. So we know the general formula that governs this kind of exponential decay is A of t equals A0 e to the kt, correct? So notice that I do have a future amount of so our present initial at 9 years, 7 grams, right? So 7. I know the initial amount A0 was 14, and E to the, we know this happened in 9 years, right? So T equals 9. All right, so substituting all those values, right, we end up with this. So if you look at this, I think you'll be able to tell me what they've actually given you without actually saying they did that, right? They have obviously given you the half-life of this particular radioactive substance, right? They don't need to name it that, and it's not of that much consequence for us because we need to still find what? We need to find K, right? But it's interesting to note that anyway, right? So without saying so, they've actually given you the half-life. So in other words, the first question they could have immediately asked you is calculate the half-life of this substance. And you should have done that instantly, right? Without doing any work, because it's given to you, because this substance has gone from 14 grams to half of that, which is 7 in 9 years. So you should know that the 9 years is the half-life of this substance. All right, but let's go ahead and proceed. So we get divide both sides by 14. 7 divided by 14 again is 0.5. So we get 0.5 equals e to the 14 divided by 14 is of course 1. So we get e to the 9k. Now we're going to take the ln of both sides again. So on the right side, of course, ln of e to the 9k is just 9k. And on the left side, we have the ln of 0.5. So now we get, divide both sides by 9. So we get k equals ln of 0.5 over 9, right? So let's go ahead and compute that. All right, so ln of 0.5, we could have actually copied that last guy, but that's okay. Divided by, divided by 9. All right, so K is approximately Now, you know this means times 10 to the negative 2, right? So the answer is being given in scientific notation. So move this 2 places to the left, so you end up with negative 0.07. Let's go to at least 4 places for k, and then 0.2, right? Yeah. Like that, okay? So now all we have to do is answer the second part of the question. It says, to the nearest tenth of a gram, how much will be present after 14 years, right? So now all you want is A of 14, because you have K, so it's easy. So it's going to be, we'll put in the initial amount, 14 grams, right? And then E to the K, which we now know is negative 0.0702, and then times, we want 14 years, right? Like that. All right, and so we end up with approximately, so we have 14 times e to the power of negative 0.0702 times 14. All right, quick check, 14 e to the negative 0.0702 times 14, okay? So once we hit enter, we get that much left to the nearest tenth of a gram, so approximately 5.2 grams should be left after 14 years. Okay, so now I want to show you with these exponential decay and growth situations how significant rounding can be. So sometimes problems will ask you not to round to the last step, right? So keep this answer in mind. That's our approximate answer with this rounding, right? Now, if we do no rounding, watch what happens. So we get A of 14, right, is going to be 14 e to the, and I'm not going to put this, I'm just going to type that, right, the entire thing. So I'm going to get to the ln of 0.5 over 9, right, and then times 14. Okay, so now watch how different that'll be from this answer. Okay, so we are still going to use this formula, but we're going to replace that negative 0.702 with what it is exactly, which is, remember, we just got it from dividing ln of 0.5 by 9, right? So we're just going to type ln of 0.5 over 9, okay? See how different they are? There's quite a bit of difference. We're going from 5.2 grams to 4. Almost like 8 grams, right? So, all right. So, normally speaking, you may not be asked to not round till the last step, right? But even if you're not, you just keep in mind, you are going with, especially with these exponential situations, you are going to get a much better answer and more accurate answer if you do not round and let the calculator do the computation till the very last step, and that's the best way to approach it. Another thing I want to bring to your attention is that once you have the growth or decay constant, it doesn't matter at what point you pick things up. So, for example, when we wanted to calculate how much will be left after 14 years, we started with the initial amount of 14 grams, right? So what I could have done is I could have adjusted this and figured, okay, why don't I start from the 9-year mark, right? That means to get from 9 to 14, that would just be a 5-year movement from that point, right? So I could have figured out A of 5, but if I did that, I would have to adjust my initial amount because, you know, after 9 years, there was only 7 grams left, right? So I would have had 7 e to the constant doesn't change, ln 0.5 over 9. And notice that here, we're going to be multiplying by the time being 5 years, right? So we're essentially changing our main equation because we're changing the starting amount, right? So let's see. So we're going to go here and we're going to replace that 14 with 7. And we're going to go up here and change that 14 to 5. Make sure that you're doing the correct one because that those just happened both to be 14. There's no connection there. Okay, so, and notice you end up pretty much with the same amount. Okay, so doesn't matter what point you pick it up at, you still get the correct answer. You just have to make sure that you adjust for the initial amount change, etc. Of course, what we did was probably the easiest way to fly, right? Just start with the initial amount of 14 grams. All right, so remember we got the same thing, of course, here. All right, and that's how you would handle a problem like that. Okay, so try it on your own and we'll move on. Okay, here's another way you may see the problem phrased. How long to the nearest day will it take any quantity of a radioactive element to decay to 25% of its initial amount, knowing that it decays according to the exponential function a of t equals a0 e to the negative 0.071 t, where t is given as time in days here. So we were using a different unit of time here. And remember, basically, we want to know how long it's going to take for a0 to become what? 25% of its initial amount. So 25% of a0, right? Now 25%, that's basically 25 out of 100 or 1/4, right? So we start with our initial equation, in this case decay equation. So we get a of t equals a0 e to the negative 0.071 t, and we replace we want the future value to be 1/4 the present one, right? So 1/4 a0 equals a0 e to the negative 0.071 t. Notice the interesting thing is, it turns out it has no effect what the initial amount is, right? It's going to take the same amount of time for it to go from from a given initial amount to 1/4 of it, right? So whatever amount you start with, the amount of time that it will take to decay to 25% of its that initial amount is going to be the same. All right, so we go ahead and divide both sides by a0, and of course they cancel out, right? Because they just leave ones, right? So so we end up with 1/4 is equal to e to the negative 0.071 t. Now we apply the ln to both sides, right? There's a 1 here. Negative 0.071 t. So ln of 1/4 equals negative 0.071 t. Now be very careful. Sometimes students make the mistake that just because the ln and e cancel each other on the right side, they kind of drop it on the left side either. Remember, this ln on the left side, it stays. There's no cancellation. All right, so t is basically going to be ln of 1/4 divided by negative 0.071. Okay, now we're just going to use the calculator. So we'll start with parentheses for the numerator. So we get ln of 1/4, and we'll exit all of those parentheses now, both of them I should say. And then we'll go ahead and say divided by negative 0.071. Quick check to make sure we typed it in correctly. All right, so if we were to round this to the nearest, let's say what we were given, what, days, right? Okay, so to the nearest day, it would be approximately what? 20 days. So it'll take this substance about 20 days to go from a given amount to a quarter of that given amount, right? 25%, of course, remember, is 25 over 100, which you can go ahead and reduce to 1/4. Or you could have also thought of it as 25% equals 25 over 100, which is 0.25, right? Either way, they're the same thing. All right, so that's how we handle that one. Okay, so here we have an Egyptian mummy that has been discovered, and the amount of carbon-14 present in their body in that mummy is about half the amount found in living human beings. The amount of carbon-14 present in animal bones after T years is given by y equals y0 e to the negative point. Notice that's 1, 2, 3 zeros. You have to pay attention to these details. And then 1216 t. Now here, y0 is the amount of carbon-14 present in living human beings. All right, so you're going, why are we using this formula? That's for animals. Well, as it turns out, we happen to be classified under animals as well. All right, so basically what we know is that in this particular mummy, the amount was half the amount present at this time, right? And we're given that the y0 here is going to be the amount in present living human beings, right? So the amount for this particular mummy was half that. So 1/2 y0 equals y0 e to the negative 0.3 zeros, and then 1216 t, right? So dividing both sides by y0, again, we get rid of it because it's on both sides. So we end up with 1/2 equals e to the negative 0.0001216 t. And we go ahead and take the ln of both sides. And we have ln of 1/2 equals negative 0.0001216 t. So for t, we're going to divide ln of 1/2 by negative 0.00012116. Okay, so again, we'll start with parentheses to, contain our numerator. So we put ln of 1/2. We exit both of those parentheses and we hit divide, and then we put negative 0.00012116. All right, so there it is. Let's say we're rounding to the nearest year, right? So this particular mummy is approximately 5,700 years old. Notice that it's T years, right? So the units for time are given to us up there. All right, so that's basically how you would approach something like that. All right, here's some information that we have seen before, but here it is again to remind us. Remember, compound interest comes in two types: periodic compounding and continuous compounding. Basically, for periodic compounding, interest is being added a finite number of times per year. So you would use this formula. And we saw where that formula actually comes from in our other video. So A of t equals P, which is the present value, times quantity 1 plus r over n to the nt, where A of t again is the future value after t years. P is the present value, which is the value at the inception of the investment or the loan. Because remember, this formula works for both, depending on which side of the formula you're on, right? Whether you're the lender or the borrower. How many times interest is earned each year is the n, which is the total number of compounding periods, and t is the number of years of investment or loan. For this, for the general formula, A of t equals A0 e to the kt, we can specify the time, but here with this kind of business of compound interest, we're always going to be using t in years, right? So for continuous compounding, it's a much simpler interest. That's when interest is earned an infinite number of times, basically at each instant. So we use this formula. A of t equals PE to the RT. And A of t is the future value after t years. P is the present value. Again, that the value at the inception of the investment or loan. And T is the number of years of investment or loan. All right, next we have an employee wants to invest $60,000 in a pension plan. One investment offers 5% compounded quarterly, and another offers 4.25% compounded continuously. Which investment will earn more interest in 4 years? And then we want to know how much more will that better investment actually earn. So we need to decide which of these formulas to use. And of course, we see in this particular problem, we're going to be using both of them, but at different times. First, we're going to find out how much the investment, which offers 5% compounded quarterly, will pay, right? So we have the quarterly case, and we have the continuous case, right? So for the quarterly case, we know that again, we're using this formula, that's periodic compounding. In that formula, n is going to be 4. That's what quarterly means, right? It's for 4 years, so that's t. And the rate is 5, so we always use the decimal equivalent, not the percent, so 0.05. I mean, we could use the percent. It's just that the decimal equivalent is so much easier. But if you're going to use the percent version, you have to make sure you keep the percent with the 5, right? All right. And then the present value, of course, in both cases is going to be the same, 60,000. Okay, so we're ready to compute A of 4 in the periodic case, the first case, 5% compounded quarterly. So we get A of 4 equals 60,000 times 1 plus 0.05 over 4 to the power of nt, right? nt. So 4 times 4, which is what? 16. So let's go ahead and calculate that. Okay, so we have 60,000 times 1 plus 0.05 over 4. We exit the parentheses now, and we raise the parentheses to the power of 16. Okay, and then we hit enter. So just double check. 60,000, 1.05 over 416. Well, looks good. So we get 73,193. We'll go to 2 decimal places since it's money, so 0.37. All right, so that's how much there's going to be in that particular investment. Now we'll go ahead and compute the continuous case, which is going to be offering 4.25% compounded continuously. Same initial amount or present value, right? 60,000. And same number of years, but R is different. Remember, move the decimal 2 to the left and remove the percent, so 0.0425, right? All right, so we get A of 4 is equal to present value, which is 60,000, e to the power of RT, so 0.0425 times 4. All right, so 60,000 times e to the power of 0.0425 times 4. So we get approximately 71,118.29. Okay, now I mean, we could sit here and figure out what the interest is, right? Because remember, that's the total amount that's going to be available at the end of the investment. But 60,000 was yours to begin with, right? Or the employees to begin with. So that's not all interest. If you want the interest, you would have to subtract 60,000 from this amount and from this amount, right? Which is easy enough to do. But do we really need to do that? Well, no, because if I want to know how much more that investment is paying, all I need to do is go ahead and subtract these two amounts, right? And I'll know how much more. So I'll subtract this from that. So firstly, if you're going to answer it properly, we're going to say the plan paying 5% quarterly will pay or will earn, and here we'll put a box, in 4 years. Okay, so now we're just going to subtract. Again, we could have calculated the interests and then subtracted just those, but given that they're both starting with the same initial amount, subtracting the totals will be just as effective. All right, so 73,000 193.37 minus 71,118.29. Take a 5-second check. 73193.37, 73193.37, and 71118.29. Okay, so there it is. So it'll pay $2,075, approximately that much more in 4 years. Okay, so obviously you're going to go with the 5% compounded quarterly option. All right, so here's we have another problem to look at. How long will it take for an investment to triple if interest is compounded continuously at 8%? All right, so we know that here of our two formulas, let me remind you what they are. Okay, so remember, you have to decide which one of these applies, right? In each case, this is continuous compounding, right? So it's going to be this one. All right, so we want to know when A of t is going to be what? 3 times its present value. So it's going to be 3p, right? And we can just use p for the amount. And the interest rate is 0.08, the annual interest rate. And that's all you need. So now you're just going to substitute. So we get 3p equals p e to the 0.08t. So notice the interesting thing. The initial amount of investment makes absolutely no difference. It doesn't matter if you're going to be investing $1 at earning interest at 8% continuously, or $1 billion, right? The amount of time it's going to take the money to triple will be the same. So, all right. Here we go. So notice, because the p's will basically cancel out in this scenario, right? So you end up with 3 equals e to the 0.08t. Now we take the ln of both sides. So we get ln 3 is equal to 0.08t. So t is basically going to be ln 3 divided by 0.08. Sometimes books will give you tripling formulas and this and that. There's no need to memorize formulas. Just quickly work it out. It's much better for your understanding of the material, and you don't need to burden your brain with memorizing unnecessary information. Okay, so we get ln 3 over 0.08, and we're just going to compute that. All right, so parentheses for our numerator, ln of 3, exit both, divided by 0.08, and there we have it, 13. Say 0.7 years. All right, so any investment of any amount, as long as it's earning interest, which is compounded continuously at 8%, is going to take 13.7 years to triple in amount. Okay? All right, and that's how you do that one. All right, next we have a study from the 70s in which it was found that one model of legislative turnover in a given country's parliament was described by this formula: m of t equals 423 e to the negative 0.083 t, where m of t represents the number of continuously serving members at time t. Here, t equals 0 represents 1965, t equals 1 represents 1966, etc. So the starting point was 1965, right? Use this model to approximate the number of continuously serving members in each of the given years. So we get M. Basically, the only tricky part of this problem is, which is not that big of a deal, is that you can't just type in this for T, right? They're very specific about what T represents, and that's basically the number of years after what? 1965, right? So to find out what T is in 1970, all you have to do is go 1970 minus 1965, and you find out that it has to be 5, right? So essentially you're finding M of 5. So that's going to be 423 e to the negative 0.083 times 5. All right, and again, one of the things in this type of problem that gets people is just simply putting it into the calculator. You have to be careful when you do that, and that's all there is to it. Okay, so we have 423 times e to the power of negative 0.083 times 5. Quick double check, 423 negative 0.083 and then 5. Okay, so we get approximately 279 members in 1970. All right, so in 1973, remember, T is easy to find. We're just going to go 1973 minus 1965. And that is, of course, 8. So all we need to do is find M of 8, which is going to be 423 times e to the power of negative 0.083 times 8. So double click that, and now we're just going to change that 5 to 8. We get approximately 218 members. And for 1980, of course, T is going to be 1980 minus 1965. That's going to be 15. So we're finding M of 15, which is going to be 423 times e to the power of negative 0.083 times 15. So we're just gonna go ahead and copy that, and now replace the 8 with the 15. So we get approximately 122 members serving in 1980, according to this model. All right, and that is basically how you would approach a simple problem like that. Just remember how to find T, and you should be in great shape. All right, so we're going to do one more problem and call it the day. So student enrollment in a given city's school district has projected growth as shown in this graph. We want to use this model y equals y0 e to the kx, the standard exponential model, to find an exponential function that gives the projected enrollment y in school year x. Let the school year 2013-14, given here in the initial part of this graph, to represent x equals 0, 2014-15 then will be x equals 1, etc. So basically, notice you can go 14 minus 13 to get the 1, or 15 minus 14. Just be consistent. So if you want to know the year 23-24, for example, for which we have a data point, you can just go 23 minus 13. So this would be representing the point at 10, comma 19,930. So notice we have 2 points shown here on this graph. One is 0, 14,225. The other one is 10, 19,930. And we found that 10 for x just by going 23 minus 13, right? We could have done 24 minus 14, same thing. All right, so our general function is y equals y0 e to the kx, right? We notice y0, the initial number at the time we started looking at this data was 14,225, so that's y0. Let me write it down here. Save some space up there. All right. And we're ready to go ahead and substitute to find the value of k, right? So we know that when t is or x here in this case that we've used, so when x is 10, y is 19,930. And y0 is this amount, 14,225, e to the k times x, which as we discovered is 10, so 10k, right? So we get e to the 10k equals 19,930 over 14,225. Now we're going to take the ln of both sides. So on the right side we get ln of e to the 10k. That of course is just 10k. So we get 10k equals ln of 19,930 divided by 14,225. So multiplying both sides by 1/10, we get k should be 1/10 ln of 19,930 divided by 14,225. Okay, so our it says round the exponent to 3 decimal places if needed to, right? So let's go ahead and compute that, and we'll round to 3 decimal places. So we have 1/10, and we're going to multiply that by ln of 19,930 divided by 14,225. We'll double check to make sure we typed it in correctly. And notice that this is going to be, this is in scientific notation, so we're going to move the decimal. It's times 10 to the -2, so move the decimal 2 to the left. So approximately 0.03. now we're right. Remember, we're moving the decimal 2 to the left, so 0.03, and we're going to go ahead and round this so it becomes 4, right? Because they said round to 3 decimal places, right? So so approximately 0.034 is the value of k. Now we're ready to actually go ahead and write the general formula. So this is the continuation of part A. So our formula is going to be y equals y0, which is 14,425, e to the k, which we now know is 0.034x. Okay, so this is the general exponential relationship between these two values. All right, so estimate the year for which the projected enrollment will be 21,400. So now all we're going to do is replace the y with 21,400 and solve for x. So equals 14,225 e to the 0.034x. So we get 21,400 over 14,225 equals e to the 0.034x, ln of both sides. So we get ln of 21,400 over 14,225 equals 0.034x. So multiply both sides by 1 over 0.034 basically. So we get 1 over 0.034 times ln of 21,400 over 14,225 is going to be x. Let me separate these a little bit. So we get x is approximately, we're going to go ahead and compute that. So now we have 1 over 0.034 times ln of 21,400. I didn't put it the multiplication symbol. I want to see if it works here. Over 14,225. All right, so yeah, so it only has that issue with e to the x. All right, so approximately 12 years, rounding to the nearest school year, so it'll be 12. So basically we're going to be adding that to 13 first, right? So 13 plus 12 is 25. So the year will be our projected year should be 2025-26. And that should pretty much wrap it up for the day. So take care until our next video.